finish off a long and joyful day. Filled with information, my head feels full. We have Jamie, who is guaranteed to keep you awake no matter how sleepy you feel.
Thanks, Vicary. Sorry, I know you all want to be swimming. At least this is the only day when we have to think after 5 o'clock. Anyway, I hope to please all of you, those of you who are physicists, those of you who are computer scientists. I will try to use things from both fields, so please ask me questions about anything at any point. Hopefully I won't get halfway through my notes and be very successful. Okay, so my title very difficult to spell. Categorical syntax for concurrency. Computer scientists use this word syntax, so I thought I'd throw that in there. Concurrency as well. But I'm going to talk about things with a monoidal categorical flavour, so it will feel very familiar, hopefully, to people who are used to working with monoidal categories and complex things. Okay, so what is concurrency? Which is the strange thing. So, and I'm no computer scientist, so you guys can correct me when I say something stupid, but it seems to me the idea is that if we have a single computational agent, maybe a computer with a single CPU, and it can calculate things, and we can develop great abstract theories to understand how it's able to do this. But what if we have multiple computational agents? Maybe they're in the same place on the same computer, or maybe they're totally separate. Maybe they're not computers at all. Maybe they're different parts of a business trying to interact to produce a product or something like that. People apply these things to all sorts of things. Maybe they're different parts of a biological system. What they need to do is they need to be able to calculate things themselves and then talk to other parts, send messages, and they need to do things depending on the messages that they receive. So the study of concurrency is the study of trying to understand how these sorts of message passing situations work, how they can be modelled, and whether we can come up with an interesting, powerful, high-level language to talk about these sorts of things. So that's concurrency. So a good sort of abstraction for this, a good language for us to use, is the idea of channels. So we can imagine that we've got some computers, these computers on the internet, and they can transmit and receive on various ports, right? So if you want to, I know nothing about networks, this is total hash, sorry about that. But let's say we have some notion of ports, right? And if you want to send a message, you have to send a message on a particular port. Then if some other guy is listening on that port, he can take your message off you. But if you want to send a message to some other guy, that he doesn't know what port to listen on, there's no way you're going to be able to connect to each other. So you have to have some small amount of shared information before you can find some way of connecting up to somebody else. So, like I said, this sounds like it's about computers and things, but really people try to apply it to all sorts of things. They try to apply it to business management, they try to apply it to biology, and this sort of thing is also, I think, very close to physics, because relativity tells us that ultimately, if we want to communicate with other objects in the universe, which is space-like separated from us, all we can do really is send the messages and see if we get messages back. There's nothing we can do any better than this. If we have the ability to make use of quantum resources, maybe more interesting things can happen. But still, relativity tells us that the paradigm of sending messages and receiving them, perhaps on certain channels, perhaps we decide to encode our message in light of a particular frequency. We might tune our receivers to receive messages on a certain frequency. So this sort of formalism that seems to be rooted in computer science, even though it is, I think it's a very sort of general questions that we're trying to answer with these sorts of models.
To understand it more specific to relativity, what you said just now. I mean, if a classical space-time also...
Sure, well, relativity tells us that we can't get away ultimately from the finiteness of the speed of transfer of information. Right? We can't assume that everyone can be free, completely synchronized with all the information that they possess. Right? So I'm not saying anything deeply profound there, but right. So this is something that receives an awful lot of study in computer science. This isn't a new thing at all. Normally, one of the most popular ways of studying concurrency is with something called process calculus. There are lots of process calculi, and each trying to solve the problem of talking about describing concurrency in different ways. Some of them are more powerful than others, some of them more elegant than others. But the strange thing about concurrency is that no one of these approaches is really recognized as being the correct way to describe concurrent systems. And that's sort of strange. Samson's written a lot about this, about how this is the, what's your word, the scandal of computer science. Is this a scandal of computer science, that there isn't one definitive formalism that we can use and prove powerful things, and it will become clear that we've really understood something fundamental? Why haven't we done anything like this? Now, I'm certainly not claiming to present such a definitive formalism, but the perspective I'm going to describe, I think, is a new one, and maybe one that will shed new light on these sorts of problems. Okay, so the particular process calculus I'm going to introduce to you quickly is called the pi calculus. And this is one of the most popular process calculi, perhaps invented by Robin Milner. And I'm not even going to explain to you what the pi calculus is in its entirety. I'll explain to you some small parts of it. Okay. So, let's write something down about the pi calculus. So the idea is that we have variables w, x, y, z, for example. And these variables are going to store various pieces of data. And basically the pieces of data that these variables are going to store are going to be the name of channels, of ports, on which we can transmit or receive information. If we want to listen to some information, then we write this. This is the channel. So really x is a variable. We say that x is storing the channel that we're going to listen on. I'm going to receive some data. We're going to call that data y. The data we receive, we're going to call it y. And then we're going to do something. We call this thing that we do p. And p, in some sense, will be a function of y. Whatever we receive, the data we receive through this listening. All right, receiving here. Whatever we receive, we put into y, and then we'll do p, which is a point of y. And conversely, we can transmit data. We write this like this. So standard notation. So again, this is the channel, x, and this is the data that we're sending over this channel. And then after we've sent that data, we might go on and do something else. Now, the point about systems of concurrency is that you've got different agents doing different things at a particular time. Right? So suppose we've got some agent doing something P and some other agent doing something Q. Then what if we've got both of them doing their own things simultaneously? Then we write P bar Q, like this. We say this is our concurrent behavior operator. So this bar operator lets us express the fact that different agents, perhaps they're spatially separated, they're doing their own things, maybe in different places or in parallel. Now, we call these things terms, and terms can be modified using things called rewrites. So let's see the most important rewrite in the pi calculus. So suppose we have this particular term. So what's this saying? This person over here is transmitting some data y on channel x, and they're going to do P. This person over here is going to listen on channel X from some data Z, and they're going to do Q. Okay. Now, you notice here, the transmission and the receiving are happening on the same channel. So, they're able to synchronize, to perform their communication. They're able to link up and find each other. And the result of that, well, this guy will have finished doing his transmission, so he's just going to do P now. This other person will have received this data Y, and that data Y will replace this data Z. This variable Z here just represented whatever it was that was received in communication. So this other person is now still going to do Q, but with the data Y replacing the data Z. So Q here was a function of Z, the data received, but now we've done the communication and the data that's received is Y. That's what's going to happen. And Pi calculus is a lot more than this, but this is the fundamental rewrite that allows us to express the idea of independent agents separated from each other being able to communicate. Now, we have a few other rewrites. This one is maybe a little bit technical and fundamentally important to the notion of communication, but a lot of the other rewrites are just things that sort of make obvious physical sense. For example, suppose we have P.
Jamie, can I ask a question?
Yeah.
So you're looking at this as a physicist, right? Do you see these arrows as concepts?
Right. So I would definitely imagine a particular term as a particular statement of the way things are at some particular time. And then a particular rewrite as some particular dynamics that happens under the passage of time. And after that dynamics has happened, the scenario now looks like this. So if you like, this is the process from a computational perspective. This is a computation step. So it's a rewrite. This is called communication. There, okay. But there are other rewrites, which are just sort of things that seem to make intuitive, obvious sense. For example, suppose we have P and Q happening simultaneously. Well, that's pretty much the same as Q and P happening simultaneously. There's no distinction we want to make between these scenarios. Similarly, if we have P happening simultaneously with Q and R happening, well, we don't want to distinguish between that and the scenario P and Q happening simultaneously are happening. I was going to object to that. Similarly, suppose there's some rewrite that we can apply to transform P into Q. For example, this communication rewrite to transform this into this, and maybe something more complicated. Then we want to be able to use that to just rewrite this P, and this R, we should be able to leave it completely alone. Again, this makes physical sense. This R is some other agent doing some other computation, minding his own business. If P can rewrite the Q, then we can certainly do it in the presence of R. Okay, and finally, another example. If P and P prime are essentially equivalent, we want to treat them as equivalent, and Q and Q prime we want to treat as essentially equivalent, and if P can be rewritten to Q, then we certainly want P prime able to be written to Q prime, right? Again, this is a rewrite giving us real content, but these other statements are just things that make the whole setting make sense with the way we want to interpret it. But if you look at these, all of these axioms are enormously reminiscent of the axioms from monoidal categories, right? Already when we started talking about concurrent behaviour, if you know and love monoidal categories, you might have thought, hang on, maybe I can model this using monoidal categories. Of course, in a monoidal category, we don't write this bar. We normally write this tensor product symbol to indicate the fact that we've got two things happening independently. And all of these axioms here sort of have counterparts in the axioms of the monoidal category. So it makes you think, hang on, maybe this theory of concurrency, for example the pi calculus, maybe it really is sort of trying to describe the monoidal category that we've sort of forgotten about. Maybe there's some monoidal category hiding behind the scenes, and this is just some sort of syntactic descendant of it, where we now have to put in these funny rules that seem a bit ad hoc. Really, if in the original monoidal category, these were just coming from the standard monoidal category axioms, and it's certainly being recognised that these look like the axioms of the monoidal category. Milner, who invented the pi calculus, knew about monoidal categories, used them a lot. So it's interesting to speculate why he didn't explicitly make the pi calculus a monoidal categorical theory. I certainly wouldn't qualify to speculate on that, but anyway, but he didn't. So the challenge is there to see if we can do that.
So are you going to be picking up the objects as terms, or are you going to think of the terms as morphisms?
Right. So one reason he might not have done it is that when you try to do it, you immediately run into some problems, which we'll see, and it's difficult to make very crisp, clear statements like that. But we'll see what statements we can make. So if you,
I mean, just as on a historical point, the sort of things you did do with the monoidal categories came after the pi calculus.
So maybe when you developed this,
and was partly influenced by some things that other people have done, like Montanari.
okay. And if you've heard of the pi calculus, or if you haven't, you might have heard of the lambda calculus. The lambda calculus is sort of an analogous calculus, but for functional computation. You only have a single agent, and all you can do is functional programming. And the lambda calculus is widely recognised as a beautiful and, in fact, definitive treatment of that sort of situation. So in that sense, much more successful than any of these process calculi. And for the lambda calculus, we can exactly do this sort of categorical treatment, and it's very successful. And we end up with this beautiful observation that lambda calculus is tightly connected to Cartesian closed categories. And essentially what we can imagine what we're perhaps trying to do here is observe this success of translating the lambda calculus into the language of Cartesian closed categories, trying to do something equivalent to the pi calculus. Okay, so let's look at some. Okay, so let's think about how we might want to do that. Exactly as Prakash suggested, what we might want to do is have types somehow. These variables all contain data. Maybe this data is of some particular type, and maybe those types are objects, and maybe our morphisms are terms. These things we're constructing, and then maybe whenever we can rewrite one term into another term, so whenever we can rewrite one morphism into another morphism, we say that they're equal. That's the approach that's taken in the lambda calculus, and it works very well. So we can just try to do exactly the same thing for the pi calculus, and we'll see what happens. So let's write out a slightly more exciting situation. Okay, so this is what we're going to start with. Here we've got somebody listening on channel S for some data X and then P. This person is listening on S for some data Y and goes to Q. And this person is going to transmit some data S. Sorry, this person is transmitting on channel S some data Z. And he's going to be R. Okay, now maybe these two people could get together. This guy could say, hey, I'm sending out data Z on channel S. This guy could say, hey, I'm listening on channel S for some data. Let's link up. Give me your data. And they could leave this guy totally out of the picture. So this guy left totally out of the picture. So we leave him the same. And then we're going to apply this communication rewrite here and here. I've got the sort of sending and receiving the other way around, but thanks to this equivalence, we don't need to worry about that. and we end up with Q and Z replacing Y, and then R. We end up with. So that's one possibility, that's one thing that could happen. But maybe instead, this guy gets ignored, and the data that this guy is sending out on channel S gets received by the data that this guy is receiving on channel S, and then we end up with something a bit different. The first guy does P, but now he's received data Z, and that replaces X here. And the middle guy gets left completely alone because he's being ignored by this process. And we have R here. So the thing to observe is that we've got, starting with this initial term, we've got two completely different outcomes. In the first outcome, the first guy is completely ignored. This first guy is still waiting to receive some data that he's never going to be able to receive anymore, unless there's some sort of transmission going on in Q and R, but not necessarily. And in the second scenario, it's this second guy who's been left out in the cold. He's still listening for data, he might not ever get it. So the point is that the pi calculus exhibits non-determinism, right? If we want to compute or apply rewrites to our terms, we can't just do it however we like. We can't say, oh, I can do a rewrite there, rewrite there, rewrite there, rewrite there, because the particular rewrites that we choose to do will affect the outcome. We've seen this in a powerful sense here. So there's no way necessarily, to square this up. There's no way to make this agree. And going back again to the comparison of the lambda calculus, that's absolutely not the case in the lambda calculus. In the lambda calculus, there are rewrites similarly, but you can apply your rewrites however you like, more or less. And you can't go wrong, you can't block yourself off from some possibility because you did some rewrite for some other rewrite, and this is not an issue you need to worry about. But now this is going to give us a big problem if we try to define our category by saying the morphisms are terms, and two terms are identified, and one could be written into the other. Because then we'll identify this with this, and we'll identify this with this. Then this and this will become identified. And these two are completely different. These two represent completely different physical or computational scenarios, and there's no way we want to have to identify them. So that's the first stumbling block that you immediately run into. You just can't do this basic identification. Leave this up to the box. This is the thing.
There's no church office.
There's no
confidence.
Yes. Now, if you know a bit of even funkier category theory than monoidal category theory, you might have heard of two categories. And if you love two categories, which I'm sure all of you do, then you'll immediately see
Not as much as you, Jeff.
that they're exactly the gadgets that you need to solve this particular problem that we've run into. So what is a two category? Well, maybe I should have even said what a category is. I'm not sure if anyone said it today. So a category has objects, here you go, A and B, that's two objects. It also has morphisms. And morphisms have heads and tails, so sources and targets. They go from one object to some other object. And in a category, if you have head to tail morphisms like this, you can compose them to get a third morphism, in this case H, F composed with H, or alternatively you could run G composed with H. And this composition has to be associative, as the axiom of a category. In a two category, you have even more. Not only do you have morphisms going between your objects, you have what's called two morphisms. Normally labeled with Greek letters going between our morphisms. So if these are objects or states, and if these are processes transforming your states, these are sort of meta processes which transform processes into other processes. So this is exactly what we're going to use to try to model the pi calculus. Our objects are going to be our types, our morphisms are going to be our terms, and our two morphisms are going to be these rewrites. So no longer are we going to say, whenever any two morphisms are connected by a rewrite, they're equal. We don't have to do that anymore, because we've got this extra level of structure, we've got these two morphisms, which is a place for our rewrites to live in theory. And this is something that you can also do absolutely for the lambda calculus, and people have done this. People have produced two categorical models for the lambda calculus, and it's sort of more natural because the rewrites in the lambda calculus are important. It's a shame just to identify two things whenever one can be rewritten into the other, because somehow then you're squeezing the rewrites out of the picture. People have developed two categorical models for the lambda calculus, but in that setting, you're not really gaining anything computationally. That's arguable, but certainly because of this, because these rewrites are confluent in the lambda calculus, you certainly don't lose very much by simply identifying terms when one can be rewritten into the other, in the way that you absolutely do lose if you try to do it from the pi calculus. Okay, so the problem is, although this maybe looks like an interesting way forward, it's still absolutely not clear how this should be done. Although I sort of said vaguely, these variables have types, and they're going to be our objects, and even though I said our morphisms are going to be terms, and our two terms are going to be rewrites, it's really not clear how exactly one should go about doing that. So that's fine, this is how they call it research, rather than exactly the book. So you can sort of think about it, and try to come up with a nice way that all these structures can fit together in the two categories. So that's the sort of thing I'm going to try to present. Now, not only are we going to be working in a two category, we're going to be working in the monoidal two category, right? Because fundamentally we've got this monoidal connective operator, our concurrency connective, which lets us do two things simultaneously, and this is going to be our monoidal product on our monoidal two category. Now, monoidal two categories are quite frightening things in their full technical glory, but we luckily won't need any of that. And we're going to rely completely on a graphical calculus for monoidal categories. And in fact, we can basically rely on the graphical calculus for ordinary monoidal one categories. So let's remember a little bit about how that goes. If we've got an object, x, we represent this by a line, then we write a little x by it, remind us what that means. And we're going to think of this as a wire that's going to carry data type x. Right, it looks like a wire, that's great. Now suppose we have a morphism f that goes from some type x to some type y in a monoidal category, and this is something that we draw like this. We write a little x there and a little y there to remind us about how f is going. And then suppose we also have some g that goes from w to z. Then we can form the monoidal product, or the concurrent combination, if you like, of these processes f and g, and we'll come up with something that goes from x times w to y times z. And the point is that there's a beautiful way to draw this, which is just drawing f and g next to each other. Maybe that's something you've seen. So there you go. So this is our concurrent combination with f and g. Remember, we're going to think of our morphisms as terms. But now suppose we have some rewrite. Suppose we have some term f and some term g, and in fact let's say we have some h that goes from x to y. So h goes from x to y, the same as f goes from x to y. Maybe we have some interpretation of these in terms of terms in our pi calculus. Maybe we have some rewrite mu goes from f to h. Then the way we're going to represent that is we're going to say, well, we start with f, that's our picture of f, and then our rewrite mu is going to change the picture that we've drawn. It's going to literally rewrite our picture and give us a different picture. So these are the two morphisms in our monoidal 2 category. So if we've got a monoidal 2 category, we can draw that by having objects being wires, morphisms being boxes, like this, and two morphisms being rewritings of our pictures, ways to change our pictures. So if you like, it's a sort of movie version of the graphical calculus. You're not looking at still pictures, but you're looking at things which evolve with time. So okay. Now here we have axioms that say, suppose you can do some rewrite, P to Q, then you can also do it in the presence of some other thing R. And that's absolutely an axiom that we also have. I'll leave that communication again. It's also an axiom that we have in our monoidal category setting. It's like this. Suppose we can do this rewrite. We have F to G. But suppose F is embedded in some other complicated thing, maybe like that, and still we can apply mu where it's understood that mu is only going to act locally. Yes. And we'll end up with this. So the mode of the diagram will be unchanged apart from the part mu is operating on. Okay, so now we're going to see how we can use this graphical calculus to draw what's going on in this crucial rewrite in the pi calculus, this communication rewrite. And of course, by finding a way to draw it using this formalism, what we're really doing in secret is finding a way to phrase the pi calculus in terms of an ideal two category. But we don't need to worry about that. We can just try to put our communication somehow into pictures. Okay, so the way, we can forget about this P, because this P isn't really affected by this communication. We'll just clutter up our picture. Maybe we'll just write a 1 here to indicate there's just some trivial thing happening after this data y is sent into x. And then, so first we need to draw the picture corresponding to what happens before the communication takes place. We have some data, y, which we're going to draw in terms of a line. And then we're going to transmit it on some channel X. I'm going to draw this like this. You can imagine this blob on the end of this line sort of being a beacon sending out information maybe on this frequency X, on this channel X. And then disconnected from this activity here, there's some other activity which is some person listening on channel X, some data he's going to call Z, and then he's going to do Y. So let's write this. Then he's going to do Q's. We're going to write this like this. And we're going to put a little z here to remember that the data that he receives, he's going to call z. I'm going to put a little x here, just to remind ourselves that he's listening on some channel x. And now, after this communication has taken place, what are we going to have? Well, let's do little dotted lines to represent the distinction between our agents. We're going to have our communication. And after the communication has taken place, there's nothing much going on over here at all. But over here, we have Q happening. But whereas before, Z was being input as the data that Q could use, now Y is being input in its place, because it's the data Y that's being received when this communication occurs. We have this little Y here, coming in the bottom, just as we did here, which represents this data Y. So we're going to draw this like this. So before the communication, we have these two separate agents. One agent with some incoming wire, carrying some data that we call Y, transmitting this data on some channel or some port Z. Separate to that, we have some other guy listening on some port. Sorry, that's an X, isn't it? And then separate to that, we've got some other agent listening on some port X, receiving some data called Z, and then doing Q, which is depending on Z. So Z is being fed into Q, let it do its thing. And then afterwards, really this should just going like that. Because really this data originally was owned by this person on the side. So this is how graphically we're going to represent executing this communication step. And hopefully that's something that makes really makes some sort of intuitive sense. So there are lots of different intuitions you can use to try and understand this. The intuition I like the best is to imagine, and this is I got this from Dan Geeker, who gave us a talk with lots of fantastic pictures. His intuition, although he wasn't talking about the pie characters, he was talking about other circuit diagrams, but we can think about these as being cables. Maybe they're USB cables. Okay? Everyone's favourite cable, right? And X here, this is the sort of upwards facing X. Maybe this is the female port for the, apologies for the terminology. Maybe this is the female port, and maybe this is the male port. Right, we draw that like that.
That's awful terminology.
This is the master port, this is the slave port. No, not, I've already said that. Okay, I don't know. I don't think any women work in hardware, so that's fine.
That's a very sexist comment.
Is it Laura's not here? Okay, so maybe we can really viscerally imagine this communication step is take these two pieces of wire, plugging them into each other, performing the connection. You like that, Andre, didn't you? You like that. And then after we plug them in, maybe we've got something looking like this. But that's fine, they're connected now. We're not going to disconnect them anymore, so we don't need to draw that drawing.
So is it intentional that you write P on the left and Q on the right?
No, it's a Q.
Oh, it's a Q.
Sorry, it's
ah,
a Q.
Very distorted
but that
Q.
is a Q.
Oh,
Oh,
that's
I
E.
thought that was a P. I read it as a P.
Sorry.
Okay. Thanks.
So this is my favourite intuition for this sort of calculus.
I'm just wondering what the dangling wire is.
Okay, so we want this
So
to
why does
be
Q have another wire coming out?
okay.
To
So
represent possible
Q-
future communication?
right, to represent some possible future. Right, maybe this is really some subpart of some larger pi term, for example. As often it is, because this is just communication in its smallest form, and of course often communication forms part of so much larger pi
11 wires
expression.
coming out as well.
Right, this is like could be some compound wire. Maybe this is x times y times z or something.
It's just illustrative.
Just
Now,
illustrative.
this wire, on the other hand, is not illustrative. That's supposed to be
Right.
something real.
This is crucial. This is the data. This is going to be carrying data, and the data being carried by this wire is the thing that's effectively going to be communicated from this agent to this agent by the application of this two-cell. And that's indicated, hopefully in an intuitive way, by how this graphical calculus operates. And just to belabor the point, whenever we manage to formulate something in terms of a movie of our graphical calculus, we exactly, as long as it satisfies some nice properties, manage to formulate in terms of the monoidal 2 category. Again, we don't need to say monoidal 2 category everything. Okay, now Q here is clearly pretty incidental, right? So let's say we've got some more fundamental rewrite. Maybe we call this X communication, because it's communication over this channel, or maybe this cable end shape, which we call X. And it does this. Right? Suppose we got that. Now suppose we really take seriously our idea of these being USB cables, and suppose we think to ourselves, you know, I'm trying to plug my mouse into my speakers or whatever I'm trying to do. My cable isn't long enough, I want an extension cable, okay? So, just for fun, how might that look in our calculus? Well, we start off, we haven't got anything at all, then all of a sudden, we've got an extension cable, okay? So that's how that might look. Just trying to take these sort of pictures and our slightly silly interpretation seriously. But then what if we build these into...
So your rewrite seems to be dynamical steps. So this one is not.
This is a dynamic step. So let's go back to the pi calculus. Let's think of this in terms of the pi calculus. Let's write x here. Let's write x here. And let's put some label, other bound variable in here, y. This isn't something that people ordinarily do in the pi calculus. That's fine. We're just interested in process calculi in general. This is still something that makes computational sense. This says we have nothing. We just have the trivial term, nothing at all. And this says we listen on some channel x, get some data y, and we immediately transmit it on some channel x. So as a pi term, we would write this as x, y, dot, x bar. Okay? This is a pretty useless pi term to be sitting around by itself.
How do you use the pi term? What's the identity?
It's the idea, yes.
Oh, well, I would argue
Well,
that it's
actually,
the
that's a
identity.
tricky point,
It's
because
not
you have a
equal.
delay, you have a delay there, so that,
Under
So
the-
this is very similar to 0, but under some...
Under the standard, I wrote lots of congruences down here. There's none of these congruences you can use to rewrite this into the identity. You have to use some communication step to eliminate it, but that's not.
yes, and you've
But
got,
it's not congruent to 0, which is how I would think.
Like the
It
inert
is.
Is
process.
it congruent to 0?
Yeah, I think in the standard pi calculus, yeah. But some other calculi, no. If you add the... I think if you add the check for inequality, for example, it's not anymore. Or yes, I don't remember, so...
Okay, well anyway, so luckily
no,
we're
I
not.
believe this isn't congruent.
To 0?
Or maybe this is the asynchronous pi calculus, yeah. Maybe that's the idea.
Okay, well anyway, luckily we're not here slavishly trying to reproduce the pi calculus. We're using the pi calculus as an inspiration. And like I said, this is the whole point of these high-level models for concurrency. There is no widely accepted best model for concurrency. If there was, we could take that and we'd better do our best to represent it faithfully, categorically, because we know it's the right way to do concurrency. But we don't have that. So if we start with some particular model for concurrency as our inspiration, and maybe it gets changed a bit, or we can do slightly more, slightly less, who cares? We're just trying to embed some high-level language for concurrency inside some sort of categorical framework. It seems maybe that's where it should be. Anyway, so let's say we can do this.
Just to say that, for example, I mean, these kind of copy processes or repeaters have, of course, been considered because they are very natural building blocks. For example, they were used to represent axial links in modeling groups of linear logic, which is quite close to categories that correspond to linear logic.
So we've got this guy that we called communication, X communication. And let's call this guy X. X for extension. We're taking an extension cable out of our drawer, right? Now let's think, when we use these communication and extension rewrites together to do something still pretty straightforward, but at least not entirely trivial. So here's one thing we might do. We might have some picture like this. So these boxes are always going to be labelled by X. Let's say this is labelled by some data Y. This corresponds to the pi term listen on X for some data Y. And then suppose we apply our X extension rewrite, and out of our box we obtain an extension cable. There it is. And now, suppose we apply our communication rewrite. Plugs three ends, male and female ends of our cables in together. And all of this, at every stage, you can write down some pi term that the pictures correspond to, and these rewrites, these two morphisms correspond to standard rewrites of the pi calculus. This is our X communication or connection. Now, if this was a pretty useless rewrite, then this is certainly a pretty useless compound rewrite, because we've ended up with exactly the same as what we started with. This is just listening on X for some data. This is just listening on X for some data. We've done something a bit funny in the middle, but that's basically pretty irrelevant. So imagine we're comparing two huge pi calculus reductions, and two huge pi calculus rewrites, where we're doing all sorts of complicated stuff, but just inside one part of it, we see that we're doing this. We would be completely within our rights to replace it with just the identity rewrite. Agree? Because it's got absolutely no interest to it, we're not doing anything really of any computational significance. But remember, we're seeing these rewrites as morphisms in our two category. So we might say we want this to express that intuition we were just talking about. We want to say that this equals the identity rewrite. This is something that we might well want to assert.
I'm getting three categorical on my count.
No, great. Great. Okay.
So, but I mean, you're rewriting rewrites, right? You're rewriting two
No, well, not quite. I've got a rewrite here, which is a two-morphism. I've got another rewrite here, which is a two-morphism.
You've got
I'm
something
asserting. No, may I? No, I'm just going to assert that they're
equality.
equal. Assert that they're equal.
Yes. In the end, the arrows have to end up in equality. So
Right, right. So just as if when we form our categorical model for the lambda calculus, we say that two terms are going to be treated as equal morphisms, if one can be rewritten somehow into the other. Here we're going to say that this rewrite is going to be, we're going to assert that that's equal to this other rewrite, because we're not interested in the distinction between these things.
You're going to set up a little active system for equality of two cells.
Right, for example. But remember, this is something that can only be used when we have exactly this, basically this, because of our rule that says, I've still got it, because of our rule here that says whenever we can do some small rewrite to some part, we're also allowed to do it whenever we have some larger system. So whenever we see this happening in some large term reduction, we're going to say we're allowed to replace it with this more straightforward reduction. Okay, now there's one other thing, which is very similar, on the same lines. I'm just going to rewrite that one quickly just so we can see it. This other one. Let's just write down there. And now I'm going to write something similar. Okay, so this is our X'd rewrite, and this is our communication rewrite. This is our X'd rewrite. This is our communication rewrite. Now, these are two equations that I've written here, and these are incredibly famous equations in category theory. Andre, stop reading your book. Tell me what these equations are. These are exactly the equations which say, let me just see what, because I've written it somewhere else. These are the equations that say, like your category theory, that this is left adjoint to this. It's precisely no more, no less than what they are. Now, if you know category theory, it would be a nice thing. If you don't know category theory, but you know pi calculus or process algebra, that should also be a nice thing, because you'll say, this is something that's very natural from a pi calculus perspective, and it already has a name in category theory. So this is something that should help to persuade you that category theory is a wonderful language that you should learn. So Andre's still shaking his head. I think he disagrees with me.
As usual.
Right. So this is called an adjunction, but this isn't a symmetrical thing. So we say that this is the left-hand part of the adjunction. This is the right-hand part of the adjunction. And we put this funny asymmetrical turnstile symbol in the middle to represent that. So we can step back from this a little bit and say, what's the point of this? What do we sort of achieve by thinking about things in this way? Well, we could say that whenever we have some particular two category that somehow whose objects are the actual sort of physical substrates that might be performing some sort of concurrent computation. And I unfortunately could give you an example, a particular example of such a category, but if we had such a category with objects, monoidal two categories, sorry, with objects, morphisms, and one cells, and then suppose we found some object X, and that's T, and then suppose we found something which we call X, goes from I to T. So that's this thing here. We start with nothing, back I, and we end up with T. That's this box X. And suppose we start with something else, which we call X bar, because that's after all the pi calculus terminology for transmitting. Suppose we have some X bar, goes from T to I. Then we can, and suppose we check and indeed verify that X and X bar form a junction in our monoidal 2 category, then we can treat this as modelling some small fragment of the pi calculus, the basic communication fragment.
Well, but the parallel concept, the concurrent composition was done in terms of the tensor, isn't it? And you mentioned
Absolutely, okay, that's an excellent question. So this is where monoidal category theory comes to our aid, because all of those sorts of things are completely taken care of. So let's see how that works. So, it's absolutely right. So, let's draw out again a direct interpretation of our initial concurrency rewriting the pi calculus. So let's write this one out first. We have some data y, that's the thing that we drew earlier, and then we're going to transmit this on some channel x, or in our table notation we're going to get this ready to plug into something else with some cable n that looks like this, and then totally separate from that we've got some other person who's waiting to receive data with the complementary cable n, meaning it's the same channel, x and x. Then they're going to do some Q with it. We'll draw it like this. But because we say that we're in a monoidal 2 category, we're guaranteed that we have rewrites available to us which just move these things around, that can float however we like. We're always guaranteed that we can do this. And see how this looks. So we're completely within our rights to rewrite this. Rewrite this like this. Okay. So does this maybe answer your question? Because we're saying we want to be in the monoidal 2 category, right?
I'm just trying to understand
The structure underlying the monoidal 2 category, you could go into enormous, considerable detail, and in fact it's only in the last year or two that for the first time anyone's ever actually written down in one document what the axioms are of the monoidal 2 category. It's really a fearsome thing. Luckily we don't have to worry about this because of this picture calculus, and as part of this picture calculus this says we can move things around topologically however we like. We have all of the sort of topological rewrites available to us. We can do all sorts of crazy things. We can let this go all around like this if we wanted to. Do all sorts of crazy rewrites if we wanted to.
In order to move things.
Okay, that's true. So that makes it something very strong. I'm saying here we're in a compact, symmetric monoidal 2 category. That's fine. We can just assume whatever we want to make our theory work. But we don't need to use these sorts of crazy topological rewrites. In fact, we can imagine, if we like, that these are cables really embedded in 3D space. This is really a picture of some cables lying on a table. And if these cables were lying on a table, you would certainly be able to rearrange them like this. So this one went over this one, over this one. You can just pick them up and do it, and put them back down again. As long as you're only doing topological deformation, you're not breaking anything, plugging anything.
I take one of your cables to the male and female and then plug it into it.
Ooh. I wouldn't want to do that. That sounds crazy. Okay, so you can do things like that, but remember here, we're just talking about the trivial sorts of things you can do. You could do something like that. That would be a That would be a non-trivial thing we could do. In fact, that would be an instance of using our communication rewrite. Let's just turn this into this.
And for you to take on back, right? So that means I.
Right, so you could do that. Well, then you get a. So if you have something like this, which is maybe a truer direct representation of this scenario here, this is this sitting next to this. This is our divide between our agents.
So, I mean, just to be clear, you wrote columns there.
It's just
right?
for communication.
Yeah, I mean, but those two things, one above the other, is that a tensor product or?
Yes, absolutely. Because this
So we can move things
of
around as
this
well,
is canonically isomorphic to this. Just as these two things are equal morphisms in the monoidal category. If we just assume that we had some morphism X going from the identity to T in an ordinary monoidal category, and some morphism X bar from T to the identity in a monoidal category, you would agree with me immediately that here, where we've got X bar here and X here, would be equal in a monoidal category to this different. Right. This is just standard application of the graphical calculus. We have something a little bit weaker now because we're working in a two category, so we don't say these are equal pictures. We say there's a little movie that lets us turn this into this. And if this is a sort of trivial invertible movie that we can do however we like, and we guarantee by coherence equations, it's never going to mess anything up.
So in ordinary diagrams, you'd have these couplings reducing the angle. Is that kind of not necessary anymore? Is it just automatically built
No, I
in?
guess it's not necessary, and that's something that would make sense to require. Sense to require, because of this interpretation we're having, that we're looking at cables on a table. This is going to be our interpretation of how the pi calculus is operating, and different channels are going to mean different types of cable ends that we have. So if we've got some guy, so I'm almost out of time, so let me finish by just writing out some sort of, maybe a little, slightly more complicated example. Maybe users achieve something slightly more interesting. So let's introduce a new channel. Let's call it Y. Channel.
It's almost 6 o'clock.
Yes. Yeah, we'll finish very soon, maybe. And we're going to. This is going to be a different channel for the same type of data, and we're going to represent it like this. So this is a different sort of cable. This is going to be receiving data on channel Y, and this is going to be transmitting data on channel Y. Again, we're going to assert that we have no junction, because this is exactly our rule for saying that for our interpretation in terms of receiving. Now let's say we have some slightly more exciting scenario. Maybe we have this.
Every variable is going to have its own shape. Every channel.
So here we're just in a tiny fragment of the pi calculus. If we receive some data, we can't use it under what I've presented to interpret it as the name of a channel and then transmit on it. You can do all those sorts of things, but then you need extensions and more structure for this sort of thing. If you give me an infinite amount of time, I'll explain possibilities of how doing this. So this is just a very small, albeit non-trivial fragment of the pi calculus. So let's say we start with some particular term like this. Let's explain this very quickly and then I'll finish. Okay, now, this picture can be perfectly represented by a pi calculus term. Here, we're transmitting some data on channel X. So this is an X bar. This is something that's going to look like X bar in pi calculus. And here we're receiving data on channel X. And here we're receiving data on channel Y. And here we're transmitting data on channel Y. And there's lots of ways this could be rewritten in the pi calculus, this complicated term, and we can investigate them, I think, much more straightforwardly by looking at the picture. So one possible thing we could do is we could allow this and this to communicate. And we'd end up with this. That's one possibility. Another possibility is that we could allow this and this to communicate. And then we'd end up with this. Now, is there a third possibility? Is there a way? So, in this one, this incoming data has been output to this agent here. In this one, this incoming data has been output to this agent here. But what about this poor guy over here listening on the wrong channel? What if he wants to receive this data, or she wants to receive this data, then transmit on this channel X? These guys aren't going to fit. This guy's transmitting on channel X, this guy's receiving on channel Y. How is this communication going to take place?
By an adapter.
By an adapter. Luckily we have this down here, which is also something that makes perfect sense in the ordinary pi calculus. We can first do a rewrite here on this bottom half, giving us this. And then we can do a further successive rewrite and end up with this. So that this data that was incoming from the input Y at the bottom has found its way through, come out to this output Y here. And so this is a slightly more exciting example of non-determinism in action in the pi calculus in exactly the same way that we saw with that conventional pi calculus rewrite diagram before. We started with one particular term, and we found different ways to rewrite it, which are completely different. We don't want to treat these as the same, and we're not treating these the same. They're different possible results from rewriting. In other words, these are all parallel one-morphisms in our 2 category, but they're not isomorphic, probably, under some good faithful representation. And we can nonetheless find them as different target rewrites from our initial term.
If the definition of the model 2 category has just been worked out, what about actually descriptions of the free such and so forth? Because I mean, one issue is, how does one even know this is going to be consistent?
Right. Well, luckily, the free such things you can be strictified very heavily. What that means is all of this nasty stuff, like what if you move things around, do certain things in certain ways, you can ignore all of those subtleties to a great extent. And in fact, what you can do is you can start by just saying, I want a free monoidal category on some basic equations. So the equations that we had, equations like this, say that something is adjunct or something else, and you can exactly form a free, say, symmetric monoidal compact closed 2 category on this data. And then you end up with exactly what you want. You end up with a 2 category in which the only morphisms are things like this, and the only 2 cells are rewrites like this, using the adjunction structure, and everything works in and those sorts of, there are theorems that basically say, don't worry, it's okay, things work out like this. There are theorems that take the real definition of a 2 category. So that's it, thank you very much.
There is also, I mean, one of the things with this kind of way of formalising these things, which I think also appear in the, I mean, there are things that, as we've discussed, that sort of bear some relation, although I think there are some very nice ingredients here, but I mean there's sort of like action calculi and so forth. So one of the things that can happen there is, which I think would happen in what you were describing, is that the full force of the sequentialization you have in the dot of the pi calculus is not being captured here. You can have reductions under the dot in the same way as one speaks of reductions under the lambda, which of course in lambda calculus is kind of considered okay because it is confluent, although in sort of more operational views of the lambda calculus you kind of rewrite from the top down. But you see what I mean? You could have several things that are supposed to happen
Yes.
in a certain order, but as soon as anything can fire, it can.
Yes, it's absolutely true. So there are certain sequential things. If you had this, for example, and you represented it in this form, you would be unable to stop this synchronization happening till after this synchronization.
Oh.
That is true. This is something so this is another reason why this is certainly not exactly the pi calculus that we're coming up with. Right, but hang on, these are, what is this saying? This is saying list on channel X for some data Y, list on channel W from some data Z, and then do P, which will depend whichever on Y and Z.
But W could be Y, couldn't it?
Okay, so I know, I'm assuming here that these are completely
What about
independent variables.
What about
If there's some interaction here, then absolutely the calculus wouldn't allow you to do one after the other if that just didn't make sense. And we can go into detail how.
I think by adding more structure, it's plausible that one might be able to bring some. If you get enough compositions in.
But certainly in the case that these are all independent. Certainly in the case that these are obviously bound variables. Different. In the case that these are independent variables, certainly in the pi calculus, this has happened before this. Certainly in this categorical presentation, you cannot stop that happening before this.
No.
But in that scenario where these are independent, you're not. I don't see that you're necessarily losing anything. Although it's certainly a different one. And maybe there are more complex ways, such as how you can sort of encode polyadic communication and monadic communication. For example, there are tricks like that you could do to enforce sequentiality where you can use it. That's the sort of answer.
So, there are many things I would like to ask, but probably they will take weeks.
Yes.
And so maybe we should stop here. Thanks, Jamie, again. So Jamie, I need to